All right, hell yeah. So what we're going over is rotational, problems from the F equals ma perspective. And you have this, and from F equals ma, well, your forces are balanced in the y. You know what I mean? And so you have there's no acceleration in the y. But we know that if we have this, whoa, this thing's going to spin, and so we know that's due to the moment. And then we know in literature, you know what I mean, and it might be written like this. Some of the torques in my physics book, they don't call it moment, but we're so used to using moments in statics that, hey, if the moments aren't equal to zero, then we're going to have a net moment. And so we're going to use the same concept of like, well, hey, well, what the hell is a moment? So if we have a moment is force times distance. Well, we just said force is equal to ma, so a moment is going to be mad. So that's where that comes from. And this is using the F equals ma approach to figure out, kind of this I alpha term. And so we set this problem up as like, well, let's just concentrate all the mass out at the very ends. And then we have this is 1 meter across. So that's what we do here. And we're going to have the same force on this one, and we're going to call this, the whole system is going to be 2 kilograms. But we have 1 kilogram of mass here with a force on it. So we're just going to cut the problem in half and say we have a 1 Newton force on a 1 kilogram mass and at a distance of 0.5. So if we look at this, the moment on this is force times distance. That's 1 times 0.5. So we get a moment of 0.5 Newton meters. That's equal to MAD, the mass acceleration distance. So we have the mass and we have the distance, and now we get an acceleration of 1 meter per second squared. Cool. The definition of acceleration is change in velocity, change in time. And this is going to be the average acceleration. Well, actually, in this case, it's literally going to be the acceleration. If we put that force, doesn't matter if it's going around in a circle. This will accelerate by 1 meter per second. This will be its acceleration. And that means at time, at 0, we have no velocity here. Velocity is 0. But by definition of acceleration, if we go to time 1 second, this says we're going to change. And so if you look at this, it says meters per second per second. That's the units on acceleration. Change in velocity 1 meter per second every second. So at time is equal to 1, we're going to have a velocity up here of 1 meter per second. Now, we use the concept that if we started at 0 and then we got up to 1, our average velocity is 0.5. So if our average velocity is 0.5 meters per second, over a course of a second, we go 0.5 meters. If we go 0.5 meters, this is our radius of 0.5, we're going to be like up there. Hey, that's 1 radian, definitionally. And then we say we want to know our angular velocity. Well, we know that angular velocity is change in angle, change in time. Same concept. We're at 0 angle in radians up to 1 radian. So our average angular speed is 1 radians per second. We did that over the course of but that's our average. So we want to know our max right here. So this is our at t is equal to 1 second. Well, we know that that's going to be double it. It's going to be 2 radians per second. So then we can find our acceleration. Definitionally, angular acceleration is the change in radians per second. And so we went from 0 radians per second up to 2 radians per second. We're going to have a 2 radian per second increase in, that's going to be our angular acceleration. So cool. So we've just identified using the MAD that we've found an angular acceleration. And if we go back to the fact that moment is I alpha, well, we have on this side 0.5, and then we're going to say this is 2. So now, what's a second moment of mass? Second moment of mass is identifying this mass, and then it's distance squared. So we got 1 kilogram times 0.5 meters squared, and this term is going to be 1/4. So there you go. We got 0.5 is equal to 1/4 times 2, and we have a check on reality that moment is equal to I alpha. Now, that was my rundown in under 5 minutes. And the same thing right here. You have the two masses at, so the moment's going to be 1 Newton. A couple is just the force times the whole distance. It's the same thing as taking halves and adding them because they're going the same direction. And then you have it equals to 2 kilograms, or the MAD. mass, acceleration, and then the distance is that. So anyway, so it's going to be the same acceleration. That's why we take the problem from here. You're going to have the same acceleration on either of these masses. That's why you can cut it into half. Heck yeah, and I don't even know. That was still a kind of a fast, shoddy way to get there. But at least now you can watch this whole video if you want. But I do the slow roll process to get there. We make some mistakes along the way. The big mistake is I call that this is 0.5 radians. That was a mistake. No, the definition of a radian is if this is the radius, you drape that string of a radius around the circle and you get to there. Cool. So 0.5 meter arc length is, if your radius is 0.5 meters. If your arc length is equal to your radius, that's the definition of 1 radian. So you can catch that error, and so now you can watch the whole video. I don't even know if it's 2 or 2.5 hours long. It's way longer than it needs to be, but that was the 5-minute approach. So thanks for joining me, and that's a video. Alright, hell yeah. So we're going to learn about rotational problems, you know what I mean? And and from the F equals ma, you know, this is our gold standard. This is how we did like statics. So we're going to go from like the statics perspective. In statics, you have the equation that said, hey, the sum of the forces are 0. But we actually have an equation for this. You know, it says the sum, sorry about that, sum of the forces is equal to mass times or acceleration, and it's kind of the sum of the acceleration, because you have a vector. A force is equal to mass times the acceleration, and because force is a vector and acceleration is a vector, mass could be a vector, but it's the same everywhere. You know, it's the same in each direction. It's the same in every location, for the most part. And so this equation basically says, hey, if you have the sum of the forces in the x must equal mass times the sum of the acceleration. Or, I mean, and not even the sum. Basically, just summing the forces equals to that mass times the acceleration in the x. And so there you go. You can sum the forces in the x direction. And then basically you're going to get a net force is going to cause acceleration in the x. And you can get an equation for acceleration in the x just by taking that net force divided by that mass. Cool. And then from statics, we just say, well, we're not, like, hey, we have a bridge and nothing's moving. You know what I mean? That's why we have, so this side of the equation, whether it's, you know, f of y is equal to mass ay, or f of x is equal to mass ax. Forces in the y is equal to acceleration. So the acceleration in the y is 0, acceleration in the x is 0. Basically, force is equal to mass times acceleration is 0 for statics problems. Now, and then we'll just simple motion. If I have a block and I do of some sort of mass and I do have a net force on it, you know what I mean? And a real easy way to look at this is like, hey, if I'm the mass and I jump off a cliff, hey, I'm going to have a force on me. And then we determine, so we use F equals ma. We use our books to figure out what in the known universe, you know, causes force. And we say, well, we have a big Earth underneath us, so this is the force of gravity. And so that goes into this side of the equation. And we can say force of gravity is gravitational constant, mass of me, mass of the Earth, radius of the Earth squared. Okay, so, and then we can throw that into this side, and then we can find our acceleration. And you can say, well, this is going to be in the y direction, and we're not going to have any forces, so no forces in the x direction. So we can say, hey, forces in the y is acceleration in the y. So we can rearrange this for acceleration in the y, and what do we get? Well, we just divide this by mass, and we get g, mass of the Earth, radius of the Earth squared. And this is just 10, 10 meters per second per second. That's the acceleration of gravity. And anytime that you're using acceleration, please just write figure out the definition of what acceleration is. Acceleration is change in velocity, change in time, dv dt. But written like this, it's going to be a change of 10 meters per second, change in velocity of 10 meters per second every 1 second. So this is going to be kind of the fundamental of how we find out that, hey, this had a velocity of 0 when we jumped off the cliff, but 1 second later, what's the velocity at t equals 1? Well, we have an equation for that, and it says our velocity is going to be 10 meters per second. Booyah! So that is going to be, and then so in this case, we don't have something that's static. We have a net force, because there's no balancing force. Unless you're going so fast that these air molecules are providing a force of drag that's equal to the gravitational force. But even at that case, sure, the force net is going to be 0. But all that means is that acceleration is 0, and the definition of acceleration is change in velocity, change in time. So if this is 0, we have a change of velocity of 0 meters per second every 1 second. So if we already, at terminal velocity, if we're already going like 55 meters per second or like 120 miles an hour, cool, we're not going to have any change in velocity, but that means either way, we're not going to have a change in velocity that slows us down, we're not going to have a change in velocity that speeds us up. So great, we are just stuck going 120 miles per hour, and without a parachute, that sucks. And so, okay, cool. So that's kind of the... so now how does this apply to this? You know what I mean? And you'll never see this like this, which is a real bummer. Sum of the moments is equal to moment, this is mass moment of inertia times angular acceleration. In my textbooks, it'll just say sum of the torques. You know what I mean? They take something that's very common to statics, and that's kind of your building block. But then I hate it how they just kind of throw away, not really, but they just label it something completely different. They're like, well, if you do have motion due to a moment that causes motion, we're going to call that torque. But it's the same thing as just having a moment. So we're going to at least let you know that sum of the torques is equal to I alpha in my textbook. But we want to go from, well, what does this say? We all know that the sum of the forces is equal to 0, and we also know that force is equal to mass times acceleration. But and then in statics we know that the sum of the moments have to be 0. But what the hell is that equal to? You know what I mean? And over here, we just have to assume it's equal to I alpha. So that's what we're going to prove. We're going to show that the sum of the moments, you know what I mean, and pick a direction. Well, and then moments operate like, moments cause rotation. So yeah, let's at least draw a square. And there you go. We have a center. And we're going to put a force on this square like this, and we're going to put a force on this. So it's a perfect, and we're going to say, hey, this distance, this whole distance right here is 1 meter, and our force is 1 Newton. Okay, sweet. We have a force of 1 meter, and here's our origin. Now, if you really wanted to, we should all just know, or professors will make you know, it's like, hey, this is a couple. You have identified a couple, and the moment of a couple. So if we say the moment about O is going to be equal to the force times the distance between the couple. So it's just that force, and we're going to say, hey, this is D. This whole distance is D. So it's just FD. Now, and in this case, our moment is going to be 1 Newton times 1 meter. So we have a moment of 1 Newton meter. Cool. That's our moment. Now, if you wanted to take moments about O, you could use the right-hand rule and be like, okay, we have a positive 1 Newton with a torque of 0.5, with a distance of 0.5. So anytime you're doing moments, just think of a wrench. And you're wrenching on a bolt, and you put a force this way, and you have some sort of distance. Well, heck yeah! If you have what's 100 pound-feet, you know what I mean? And so if we're putting a force of 100 pounds, and we have a distance of 1 foot, heck yeah, we have 100 foot-pounds. You know what I mean? That's the torque of a lug nut. And so there you go. So in essence, this force operates through this line of action, and we have that force of 1 Newton, 0.5 meters away from the origin. So heck yeah. So moment about the origin is a positive 1 Newton times 0.5 meters. But then this one, same thing. Line of action right here. Distance from is another 0.5. So we have another one of those. Plus 1 Newton, 0.5 meters. So these add up. This is 0.5 Newton meters. 0.5 Newton meters. And those both add up to 1 Newton meter. Okay. So, I mean, I guess it's good to go over the basics because we're going to take this and usually you're just like, well, hey, the moments are usually equal to 0 if this is not moving. You know what I mean? If we observe this square is not moving, well, we have to actually put an opposite torque on, and so sometimes you'll see this. You know what I mean? We're going to put a force that way because this is downward, and then, so yeah, so now we're going to put a force F prime on this, and then these, if they're operating the same distance, F prime has to equal F, you know what I mean? And these are both 1 Newton. Alright, so, and that's what we do for statics. But now we're going to say, whoa, we actually, we don't have those two forces. So we actually do have a net moment of 1 Newton meter. And we do know that this is going to cause rotation. Just by definition, having a moment is going to cause rotation. And then if we do the sum of the forces in the y, so here's the y direction. Sum of the forces in the y is equal to mass times acceleration in the y. Well, we have 1 Newton up minus 1 Newton down is equal to mass times acceleration in the y. We have 0 newtons is equal to mass times acceleration in the y. So it looks like acceleration in the y is going to be 0. So here is a case where we identified that we're not going to have motion in the y direction. We're not going to have a change in velocity in the y direction. We could do the same thing. There is no forces in the x. So we're going to have acceleration in the x is 0, acceleration in the y is 0. But we still have motion because we know that a moment. And if we don't have acceleration in the x and the y in a 2D scenario, but we do have a net moment, well, guess what? It just means this thing's going to spin. And I think we can see that. You know what I mean? We're putting a torque on this, and it would be like putting two little rocket boosters, and then I got to put these in the right direction. So if we're putting a force that way, heck yeah. So the rocket boosters would be right there, and you know, shooting out right there. And this thing is just going to start spinning. It doesn't even need to be pinned to anything. You know, that's the thing is because we don't have any net forces pushing it, you know, one way or the other. So we have pure rotation. All right, so now that we've identified that we're going to have rotation, well, we want to know, like, hey, we want to know something about that rotation. You know what I mean? Like, what's its properties? And we're going to use F equals ma. This is what we want to know. So let's grab another sheet of paper. We're going to draw our square. We have a force of 1 Newton that way, a force of 1 Newton that way. So we have a moment about the origin, and that's going to be, and this distance is going to be 1 meter, and so this is 0.5 meters, 0.5 meters. You know what I mean? So we have a torque of 1 Newton, 1 meter, you know what I mean, that couple, and that's going to be a moment of 1 Newton meter, and now we want to analyze this. Now, where we're going with this is just equal to I alpha, so where we want to prove this. Like, I think these are the two most bizarre letters in physics, you know what I mean, so the normal person, they're going to see this and be like, nah, thanks, you know what I mean, but if you understand that it is F equals ma, then that's the building block. You know what I mean? If you can have in your mind that everything is F equals ma in a Newtonian sense, then we're just good to go. We should be able to get an understanding of rotation or any motion, basically any motion, by using F equals ma. And so now we're going to get an understanding of how it applies to rotation. We definitely have to simplify this. You know what I mean? Let's say this just has a mass of whatever, you know. I mean, so now we have to turn this into a simpler problem. So the one that I'm going to turn it into is I'm going to say, hey, this force is acting on a mass there, and then here's the 0.5 meters, and then another 0.5 meters, and then we have another mass right there. And so I'm going to say 1 Newton, 1 Newton. I'm going to say this is 1 kilogram. Mass is equal to 1 kilogram. So there you go. So this is going to be our simpler setup. And this still, if we did the sum of the forces in the y is equal to mass times acceleration of the y, well, they're going to equal 0. You know what I mean? So acceleration of the y is 0. If we do sum of the moments about the origin, you know what I mean? Basically, this 1 Newton over 0.5 meters positive, and this 1 Newton 0.5 meters positive. Those are going to add together, and we're going to get a total of 1 Newton 1 meter. You know what I mean? Because this would be 0.5 Newton meters, and this would be 0.5 Newton meters. So that would add up to 1 Newton meter. Okay, so we've identified that we're going to have rotation. You know what I mean? And in this case, and then we're going to say initial velocity is 0. You know what I mean? So our velocity initial is 0. And, you know, how does this apply to rotation? Well, you could say omega initial is 0, so radians per second. We're going to have 0 radians per second. But we don't even have to get there yet. We don't have to involve radians yet. So we are going to... We're going to show that if we are rotating, you know what I mean, the things that we need to know about rotation, and we'll get to them actually in a second. We're going to make this problem one simpler. We're going to take this origin, and we're just going to take half the problem. Because the force, both these forces on both these masses are causing rotation, is going to be the same rotation have we just have 0.5 meters on a string of just this one mass of force is equal to 1 Newton. Now, there's two ways to visualize this. You know, sometimes it's easy to visualize. You know what I mean? Maybe you have this on a table. You know what I mean? Some sort of table, and the table is ice. You know what I mean? So it's frictionless. And this is, it can still be just a little spherical ball. And then this is a lightweight rod. You know what I mean? But even that might be too much to visualize. So the other way to visualize this is just like, hey, take it into deep space. So you still have this mass. Mass is 1 kilogram. Sorry. And then you still have a force of 1 Newton. Now, and you're still pinning it to outer space. And just pretend there's no gravity. But we are influencing this mass with 1 Newton. So we know that if this string is at that position, 1 meter, and we put a force on it, well, heck yeah, we can just use F equals ma. So we're gonna do F equals ma, and we can just call this the y direction. This is going to be positive y, negative y. And we can say sum of the forces in the y direction is equal to mass times acceleration in the y direction. So we do have a net force. We're going to have 1 Newton in the y direction is equal to mass times acceleration in the y. We're going to rearrange this because we want to find acceleration in the y. And that's going to be 1 Newton. Basically, you just divide this mass over here and get acceleration. So we're going to have 1 Newton divided by 1 kilogram. And how is this acceleration? It is good to go back to F equals ma. The units on this, and one way to... so the units on force is 1 Newton. Mass is like 1 kilogram. And acceleration is 1 meter per second squared. So if I see newtons right here, I can just change this to 1 kilogram times 1 meter per second squared, divide by 1 kilogram. And this is a very visual way to see that we have 1 meter per second squared. So we have an acceleration of 1 meter per second squared. Excellent. Now, a lot of people will get to here and they'll be like, cool, I don't know what that means. I literally don't know what acceleration means. That's why it's really important to go back to the definition of acceleration. Acceleration, I first write it in words. Acceleration is a change in velocity in meters per second divided by, or just say for every 1 second. So cool, we're going to have a change in velocity in meters per second for every 1 second. And what's our change in velocity? It's literally the number that is right here. Because this says we have a number of meters per second. So acceleration, the units on it is meters per second squared, but you can really write it as meters per second. So now you can see it's a change in velocity of meters per second for every 1 second. Heck yeah. So now in our case, we're going to have an acceleration of 1 meter per second. This means that we're going to have a change in velocity of 1 meter per second for every 1 second. So at second 0, so at time 0, we're saying that our velocity is 0. You know what I mean? At time 0. So how about this? What's our velocity at time is equal to 1 second? You know what I mean? We're spelling it out so easy that, you know what I mean, intuitively we just can't mess up. We have an acceleration of, we're going to change our velocity by 1 meter per second in 1 second. We're going to go from 0 meters per second to 1 meter per second. So cool. The velocity at time 1 is going to be 1 meters per second. But now here alarm bells must go off because... Alright, heck yeah. So yeah, alarm bells got to go off because this is where you can make your first mistake. And we got to do this situation kind of twice for this problem. So actually, when I did it the first time, I ran into the same mistake I was going to run into right now that I did a little bit later on, and we'll point that out. But if we start with a velocity of 0, and then at 1 second, we increase to a velocity of 1 meter per second. Now, we're assuming that this is, you're slowly increasing. You're going from 0 to 1, you know, over a period of time. So this is where I always bring up the example of going 60 miles per hour and driving for an hour. You know what I mean? I think everyone has like a town or, you know, that's 60 miles away. You know what I mean? A town that it's going to take 1 hour to actually get there because it's 60 miles away. And maybe your average speed can be 60 miles per hour. That's going to be your average speed. But what we're saying is, what if you treated that trip different and you started with the speed of 0 miles per hour, and then you slowly increased your speed, and once you got there, you know, you were going 60 miles per hour. But just over the course of 1 hour, you're going from 0 to 60. So what we do is you can just see that your average speed, and we want to know. The question is how long is that going to take? Whoa. Yeah, if you do this for 1 hour, how far can you go? You know what I mean? So if I'm going from 0 to 60 over the course of an hour, just slowly increasing my speed, how far can I go? Well, basically what we're getting at is we have an average speed of 30 miles per hour, and so if we were traveling for 1 hour, we only went 30 miles. Cool. So same scenario here. If we start at 0 meters per second, but in 1 second we get to a velocity of 1 meter per second, how far did we go? It's the same thing here, but just because we're dealing with 0 and 1, it's very difficult to see. But we do that same thing, you know what I mean? We start from 0 and we get to 1 meter per second, and we did it for 1 second. So our average velocity is 0.5 meters per second, or just half of that. So we got 0.5 meters per second, and what's our distance? Well, this is our velocity average, so it's like we were going 0.5 meters per second for 1 second. And again, you know, something to make velocities real simple is like, what's the units on velocity? It's meters per second. What's the units on time? It's 1 second. Alright, so we have these two. So we can do whatever we want to them, but what do we want? We want meters, you know what I mean? So if meters is up top and seconds is up top here and down below, we can just multiply these together. So yeah, hell yeah. So we're going to take that 0.5 meters per second times 1 second. Seconds will cancel, and we went 0.5 meters. So hell yeah. So even in this, we had an acceleration of 1 meter per second. That means we're going to change our velocity from 0 to 1 meter per second. Our average velocity over that 1 second is going to be so our velocity average is going to be 0.5 meters per second. Our distance that we travel, we're just going to call that x. X at t equals to 1 second, because our position at t is equal to 0 seconds is just 0. We're starting out at 0, but in 1 second we're going to go 0.5 meters. Okay, hell yeah. So now here is the first place where we introduce the concept of radians. You know what I mean? And I have a pretty good axiom to make radians fairly simple, because what we're going to do is we're going to go 0.5 meters, but we're going to do it on a sweeping arc. And so the first equation that we need to know is like, whoa, well, we have an angle in radians. And what the hell is an angle in radians? Well, I like to say if you have this angle in radians and you multiply by the radius, you know what I mean? And that'll be in meters maybe. This is dimensionless, it's just an angle. You're going to get, so radians times radius is something normal, and this is going to be your arc length. They use the term S, but yeah, this is just going to be, and it's going to be in meters, but that's going to be your arc length. For our problem, hell yeah, that was just that distance, that linear distance x. So x at t is equal to 1 second. This is how far we went. We went 0.5 meters. So it was really easy for me to set this up and be like, oh, well, in 1 second we went 0.5 meters? Well, hell yeah. I know definitionally that is 1 radian. And because you can do it the opposite way, or you can always just say radians times radius is something normal, because then the next thing we're going to do is radians per second, angular velocity, times the radius is something normal, and that's just the tangential velocity. And then again we have the radians per second squared. It's the change in angular velocity. So this is the acceleration of angular velocity times the radius is something normal. Well, that's just the the tangential acceleration. All right, hell yeah. So and then the other way to know definitionally what a radian is, and it's just fast. I looked this up in the book, and they used such crap language just to spell out something so simple. You know what I mean? So if here's your radius of 0.5 meters, you know what I mean? Cut a string to that radius, and then we obviously know this is a circle of radius 0.5 meters. So you're gonna measure a string that's equal to this radius, and then start to drape it around this circle, and you're only going to get to there. Definitionally, the angle to get to there is what we call is a radian. And if you did that just by the way a circle is, and it's like one of the equations that needs to come up way more often is circumference. And I wish, I'm just going to call it little c, but I wish there was some other cool way, you know what I mean, to be like, yeah, this is circumference, you know what I mean? Because circumference as equation, I feel like in physics a lot of people don't use it hardly at all, but it definitely comes up when understanding for sure radians, especially when you're trying to compare 360 degrees to what is a circle in radians, you know what I mean, where like no one knows. But yeah, it's circumference. So the circumference of a circle, I guess we can just call it 2 pi r. You know, it's pi d, pi times the diameter, but it's 2 times pi r. So heck yeah. So if we have a circle of 1 meter, the radius is 1 meter. We're going to have our circumference of 2 pi times 1 meter. We're going to have a circumference of 2 pi meters. Hell yeah. So that's going to be our circumference, 2 pi meters. And in this circle, with a radius of 1 meter, and if we're saying 1 radian is draping that 1 meter string to there, well, we're going to go 1 meter. Do that again, we're going to go 2 meters. Do that again, we're going to go 3 meters. And so on and so forth. 4 meters, 5 meters, 6 meters. And we're pretty much there, but we know that this circumference of the circle is 2 pi times 1 meter. So it's 2 pi meters, which is 6.28. You know what I mean? Because pi is 3.14. Double that is obviously 6's, 2's, and 8's. 6.28 meters. And we said definitionally a radian is just draping that 1 meter string to there, to there, to there, to there, to there. Well, we're going to be a little bit short, so we have to cut another string to 0.28 meters and then drape it that rest of the way. So we're going to have, so that's a radian, that's a radian, 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 radian. We're going to have 6 of those, 1, 2, 3, 4, 5, 6, and then 0.28. So we're going to have, for a full circle, we're going to have 6.28 radians in quote unquote degrees for that circle. Hell yeah. And so that's I think you can't not explain radians 1,000 times. You know what I mean? Just because it doesn't get explained enough, obviously. You can go your whole college career would be like, nah, I really don't know what a radian is, don't really care. All right, so we have that. Next thing up is, well, cool. So that definitionally gives us everything we need to know about this, how this thing is rotating, because we have these as definitions. We say that rotationally, we're going from 0. In 1 second, we're already at an angle of 0.5 radians. You know what I mean? And obviously, this isn't 0.5. A 60-degree angle is about 1 radian. So if I'm only saying we're only going 0.5 radians, my bad. The actual picture should be like right down to there. But bear with me. Okay, so we know that our angle went from 0 radians at time is equal to 0 to time is equal to 1 second of 0.5 radians. You know what I mean? So now we can, just like we said definitionally, acceleration was change in velocity, change in time, and we went through that whole process of meters per second. Now we can say that omega, angular velocity, is radians per second. That's the same thing, you know what I mean? It's going to be the change in angle in radians for every 1 second. And you know what I mean? You can't write this one enough, because if there's any one equation that hardly gets spelled out, it would have to be this one. You know what I mean? The angular speed in radians per second is a change in your angle using radians for every 1 second. And I think it would be way easier if you were just turn this into revs per second, revolutions per second, and then you just had some sort of other term. You know what I mean? I don't know what your term would be. I mean, you could do that for your term. You know what I mean? Revolutions per second, and now this definitionally is going to be and you'll have a number on this. So it's going to be the number of revolutions for every 1 second. You know what I mean? Yeah, that kind of spells itself out almost too easy, because this is more synonymous with change in angle. You know what I mean? So I don't know. Maybe just call it omega prime. That this would be change in degrees for every 1 second. So there you go. So if we do have a change in degrees of 360 degrees, if at time 0 we're here, but then like Shaun White in 1 second spins and now he's back to there, you know what I mean? He went 360 degrees in 1 second. So that is going to be that's going to be very similar to radians per second. All right, hell yeah. So yeah. And maybe that is easier to understand, where you're just like, oh, okay, I have 360 degrees. 360 degrees per second. This is the same thing as 2 pi radians per second. If you have a problem that says I'm spinning at 6.28 radians per second, you know what I mean? Either of these two, it's best to get into revolutions, you know, to have an understanding of what's going on with the problem. Because even in ours, let's say at 1 second we do have a, we haven't gotten there yet. We actually don't know what our speed is. We have only determined that at time 0 we're at 0 degrees, and then at time 1 we came up here and to 30 degrees. You know what I mean? So there you go. So our problem in kind of degrees is we went from 0 to 30 degrees. Now, and how many 30 degrees are in a circle? You know what I mean? Hey, here's 180, here's 90, and then you're going to have 30, 60, 90. So you're going to have 3, 6, you're going to have 12. So you're going to have 12 of these 0 to 30 degrees. So now I'm just going to propose, and this is going to lead into our actual speed. I'm just going to propose that every second we're going to move 30 degrees. Cool. So if we go 0, 1, you know, it'll take 12 seconds to do one revolution. So from that, we can do one revolution in 12 seconds. Holy Toledo. So our speed would be 1/12 a revolution per second. You know what I mean? That would be our speed. Now, let's go back to radians, because if it took 1 second to go a half of a radian, which is the same thing as 30 degrees basically, it's going to take 12 seconds to go, well, if this is just half a radian, we have 12 half radians. So we have 6 radians for one circle. And that's, you should always think a circle is just 6 radians. You know, at the end of the day, get rid of that 2.8. Just mentally, it's going to be a lot easier. So we're going to be moving 0.5 radians per second. And that's actually, that would be our speed, you know, just 0.5 radians per second. And that is an omega. Omega of 0.5 radians per second. That's how that would be written. And for every 1 second, you're just moving 30 degrees. So how much would it take to do one revolution? You know what I mean? Well, it would probably take 12 seconds. And so let's do that one with factor label. So if we have omega of 0.5 radians per second, what do we multiply to actually get revolutions per second? Well, we have radians up here, and we know that 6.28 radians equal 360 degrees, or 1 revolution. So if radians are up top, we're going to do 6.28 radians down below, and we're going to equal that 1 revolution. So the factor label method says these are the same, and so we have radians cancel, and now we're just left with revolutions per second. And it looks like we have 0.5 divided by 6. That's the same thing as 1/2 times 1/6, and we get 1/12. So our angular speed is going to be 1/12, and I guess I can get a, so it's going to be 0.08 revolutions per second. Okay, and so 0.08 revolutions per second is the same as 0.5 radians per second. Okay, hell yeah. But now what I'm going to say is that isn't our speed. Because if we go back to, it is the equation. You know, hey, didn't we just say, hey, omega is change in angle, change in time? You know what I mean? We went from 0 to 0.5, so we went 0.5 radians minus 0 radians, and we did that in 1 second. Yes, but this is your average. So anytime you're using this equation, just know that this has to be omega average. And you should probably write it. Like when we say acceleration is change in velocity, change in time, you're literally saying acceleration, the average acceleration, is change in velocity, change in time. This is why we make our time unit kind of small. Even 1 second usually is good enough for most problems. Where you can be like, well, yeah, I went from 0 to 0.5 meters per second in 1 second. So that was going to be my that's going to be my acceleration. Or no, for us it's 0 to 1 meter per second in 1 second. So our average acceleration was 1 meter per second. And definitionally, we know that F equals ma, going back to this, is that, hey, if this is constant, and we're going to say we have a constant 1 Newton on here, then our acceleration is constant. You know what I mean? just for our problem, this force is going to be constant. This 1 Newton force is always acting on that chunk of mass. And again, this problem goes back to having just a square chunk of mass, and you're like, hey, we want to know the rotation of it. Well, let's just make it simple as possible. Let's just put all the masses out to the ends, and then we halved it, and that's where we're at on this. So sorry we're going so slow about this one. Okay, because now we know that the average velocity is going to be, well, our change in radians. So change in that angle, we went from 0 to 0.5, an angle of 0.5 radians. And so 0 to 0.5 radians, so it looks like our omega is 0.5 radians per second. But again, this is our average speed. So now you kind of have to do this in reverse. We know at the beginning, omega initial, radians per second. This thing is stopped. So this is 0 radians per second. So it'd be just like this. This is such a good one to have. Because, hey, if we started our trip going 0 miles per hour, but then we slowly increased to 60 miles per hour over the course of an hour, like we have 3 things going on here. And beginning, we just said, hey, we know these two. We're going to go from 0 to 60, and we need to find our average speed. So that was pretty easy. But now we're going to do the problem in reverse. We know we started at 0, and we know that we have an average speed of 30 miles per hour. All right, sorry about that. Okay, so yeah, so in our case, we know that we started with 0 radians per second, but we know that we have an average, angular velocity of 0.5 radians per second. And now from this, we want to know what our max is. So all you have to do is see the relationship between the average and the max, and know that if we know this is 0, this is 0.5, then this has to be 1. You know what I mean? Because if this is 30, this is double that. So in our angular velocity, we have 0.5 radians per second, so double that. So then we know at this point, our angular speed at time is equal to 1 second is 1 meter per second. And hell yeah. So and now we're basically home free. I have like literally no more writing room, but we're going to stick on this page. We're trying to get to why this torque of 1 Newton per meter is equal to I alpha. That was going to be the torque for the whole setup. What we did is we halved it. So let's write that moment equation. We're going to say moment about this origin. So now this is just 1 Newton times 0.5 meters. So for our torque, we're going to have a moment of 0.5 Newton meters. So now we're going to say 0.5 Newton meters. This is the moment part is equal to I alpha. And heck yeah. But we want to still use F equals ma. That's why we're saying we're using this F equals ma to find the actual acceleration of that. And once we did, well, cool. Now we can figure out what the angular acceleration was. Because what's the definition of angular acceleration? That's change in the angular velocity, change in time. And again, when you write it like this, it has to be the average. You know what I mean? And so, but that's not too much of an issue. The main issue was just trying to find. That's where I messed up, because I was just like I said I used this equation to find 0.5 radians per second, and I made the mistake of just assuming that this was the angular speed at time is equal to 1, and that's not the case. That's the average speed to make that distance. If you're going that distance in 1 second, but you start out with 0 velocity, hell yeah, your speed there has to be double to make your average speed across that little distance, you know what I mean, work out. But now that we just know we know the angular speed, we know the omega initial is 0, the omega final is 1 meter per second. So, I feel like I'm messing up again. Holy hell. And I don't really have any more paper to work with. I'm just going to cut a little strip. There we go. Yeah. It just feels like I thought my alpha. I thought it was going to be 2 meters per second squared. Oh yeah. It still is. No, it's not. Not from that. All right. Well, let's go with it. Yeah. And let's catch up. So if we have F equals ma, we know that our acceleration is that force divided by that mass. We know the mass is 1 and the force is 1. So we know the acceleration is 1. That's going to be 1 meter per second every second. We're going to go velocity initial 0 to velocity final is 1 meter per second. We know that's our average velocity. So we have our average velocity is 1 meter per second. So that means that our velocity max, or velocity at time is equal to 1 second, has to be double that. So our velocity has to be 2 meters per second. Oh, we didn't need to do that. But yeah, we get our velocity average. Oh, maybe not. Well, what the hell? You know, we have a change in velocity from 0 to 1. So no, if we have this, then our velocity average is 0.5 meters per second. And then we traveled for a time of 1 second. So we go a total distance of 0.5 meters. And that's going to be associated with a radian of 0.5 radians. So that's the angular distance that we're going to travel. But we're going to start with 0 radians per second. And so we need to have angular speed at time is equal to 1 of 1 radian per second. So our average speed will be 0.5 radians per second. Okay. But this is where I'm getting hung up, and maybe just because I did this problem earlier today and kind of came across the same issue. Oh, but I made my problem different. In that scenario, I made this 1 meter. And this scenario to be 2 meters. That's where I messed up. Earlier today, that's where yep. That was the setup from earlier. So I think we're good to go. And then just angular acceleration is your change in omega, change in time. So we're gonna have 1 radian per second minus 0 radians per second over that 1 second. So we're gonna have an alpha, or angular acceleration, of 1 radians per second squared, which is 1 radians per second. That's our change in angular speed every 1 second. Okay, so there you go. So we have we have a moment of 0.5 Newton meters. We know that's equal to I alpha, and then we found our alpha to be 1 radian per second squared. So definitionally, this I has to be, our moment of inertia has to be 1/2. And so that's when we get into what the hell is moment of inertia. Moment of inertia. And is there any other way to explain this just a lot simpler? Oh, bummer. No, I mean, for this one, I get this might not be the problem to it comes from angular momentum. You know what I mean? And I think this is a good place. It's a different problem, but we're going to have 0.5 meters, and now we're going to say, hey, this has some sort of velocity tangential. We have a mass of 1 kilogram, and we want to know the angular. And so even at our time of 1 second, what did we say the tangential velocity is going to be? Because didn't we say that? we're going to have a change in velocity of 1. So our velocity final is 1 meter per second. So we know our velocity tangential at time is equal to 1 second is 1 meter per second. And now I have a boost of confidence because this is so good. I mean, we're taking the most simple thing ever and then just slow rolling it. So like you just can't mess up, you know what I mean? And you might mess up just a little bit, but you can always go back and figure out where your error is, you know what I mean? Ours was, initially today was just calling this average angular speed, our angular speed at time is equal to 1, and that wasn't the case. This is equal to 2 times omega average. There's the equation there. Okay, so we're going to say this is going to be t is equal to 1 second. Now we do have some motion. So angular momentum is like, cool. Well, you must have motion, you know what I mean? So you have some sort of velocity, you have some sort of mass. I'm sorry, circle velocity, but anyway, you have some sort of mass that has a velocity, and the angular part is, well, we're going to assess that from a certain distance. So now I think we can go back to our wrench, and so you have our wrench right here, and out here we're going to say we have a mass, and we're going to have some sort of velocity on it, and we're going to we're going to have a distance right here, or like a radius, and so from this point 0. All right, hell yeah. So we're back, and we're getting there. We're saying that, hey, we're using F equals ma to find that moment, and then we're going to prove y it's equal to I alpha. We already found the angular acceleration, and now we want to know why it's multiplied by this I term. You know what I mean? And I don't even know if I can explain that. All right, it's telemarketing season. Okay, so. Yeah, but let's get back where this I term comes from. It comes from angular momentum, and so we're gonna show that angular momentum, just as a little foreshadow, is equal to I omega. So at least we can figure out why this is a physical property of mass and distance. You know what I mean? And it's distance squared. Okay, so in this case. And you have to compare the wrench to something like normal. Typically we have a distance here and a force, and we know that this is like how our lug nuts stay on. You know what I mean? Hey, can you put a force on the end of your lug nut that's 1 foot long of 100, and then can you reef on that with 100 pounds? Cool, you get 100-pound feet. We understand that as a principle. But now, hey, can you have a mass spin around a central point? You know what I mean? Because I maybe want to use this for my bike. You know what I mean? Can you have a tangential velocity on that mass? And then I'm actually going to use that, you know what I mean, for something. We see how that is a useful parameter. You know what I mean? Whoa, if I have some sort of mass with some sort of velocity and it's caught on a string or spinning around like a pedal, then hey, this is a useful quantity. It's a useful something that I can work with. And then we want to put a number to that. You know what I mean? Because maybe if I lengthen this radius out here and have this thing go the same velocity, same mass, but just a bigger, you know what I mean? Maybe that's going to have a different property. And actually, wouldn't this one be better? Well, I don't know. That's interesting. Like obviously, this one's going to go. Well, no, this one's going to give you more leverage. Yeah, but anyway, holy Toledo. You know that's for a different video of understanding what this number actually means or its use. Because yeah, it's two different scenarios. It's like, well, is if you have this scenario, yeah. Anyway, wait. So, but yeah, there you go. So this angular velocity, is going to be just the multiplication of the distance times the mass and the velocity. You know what I mean? So if we quantify this mass and then its velocity, angular momentum is just that times the distance. Just like we quantified this force. So angular momentum is spelled out like momentum, and I don't know if the Latin word moment is the same thing when they use the term angular momentum, or maybe I'm just combining those two. But this is a moment of force. The word moment, in statics is like, whoa, you have a force over a distance. Increase the distance, you increase the moment. You know what I mean? Increase the force over that same distance, you increase the moment. Double the moment and double the distance, you know what I mean? You quadruple. It's going to be 2 times 2. It's going to be 4 times. Your moment's going to be 4 times as much. Okay, so keep that in mind, because now instead of a force, we're going to apply that mass and velocity. You know what I mean? Hey, we've identified a mass. We're going to put a velocity on it, and sure, that's it's going to be the moment. And for simple terms, we call this momentum. Mass times the velocity is momentum. That actually might mess it up with the word moment. Angular momentum. We get that. That's angular momentum is this distance. And then the mass velocity. Momentum, and this might be for a separate video. Linear momentum is mass and then a velocity. Let's say that way. Just going in a straight line. But the only way things can go in a straight line is let's say there is no straight lines. You know what I mean? So the only way a straight line can exist is if you take your radius to infinity. You know what I mean? This radius is so far away that this thing just appears to be going in a straight line. I don't know if that was useful at all. But it is, because now you have linear momentum. Well, linear momentum is the moment of mass and velocity, but when your radius is infinity. You know what I mean? So the angular momentum that's where it gets confusing, because it seems like your angular momentum is then infinite. You know what I mean? And theoretically, it is or something. But anyway, holy chill! I can't get off topic on stuff that I hardly know, because we're just trying to figure out. I don't even know where. We're trying to figure out where the I comes from. Hell yeah! So you have. Angular momentum is that distance. Hell yeah. So it's this distance and then times the mass, the linear momentum part, mass times velocity. But we know that if we do have a constant omega, this velocity, what's omega? It's in radians per second. And if we multiply radians per second times radius, we get something normal? Yeah, that's tangential velocity. So if this is the distance to the mass times its tangential velocity. Tangential velocity is radians per second times the radius. So hell yeah, you get these 2 things to pop up. This is tangential velocity. So linear momentum, this is where I don't like the fact that linear momentum is I alpha, because you're souping together terms. This is a soup of terms that was part of, half of the term came from the tangential velocity. But anyway, so, because now you're going to rearrange terms, and you're going to go R, M, R, omega, and then you might go M, R, R, omega, and then you might go M, R squared omega. But you know what I mean? 5 steps just to see, like, whoa, yeah, if we bring this term over here, and we get R squared, and then we have an M, and it's written like this, well, hell yeah. Now we're definitionally saying that this is mass moment of inertia. And again, it's good to see what moment. Bring back the moment of a force. You have a force and a distance. Hell yeah, we get that. That's the moment of a force. So now in an I-beam, you have this area, and then you have this distance to the area. And actually, for an I-beam, you do area times distance squared. And we're going to call this second moment of area. The first moment of area would just be like, okay, I get it. Let's just take this area and then times this distance. Cool, you have area times distance. It's the same thing as right here. You know what I mean? If we turn it that way, you know, you come out here, you've identified some area, and then you have some sort of distance. You know what I mean? Now this thing is just in an I-beam shape. So you're from your center, you're going out a distance, and you're capturing some area. But for material mechanics, we need to square that distance. And we call this the second moment. So the first moment is just like, this is the first moment of force. The second moment of force would be force distance squared. Okay, the second moment of area is area distance squared. The second moment of mass. So now we have mass. So now we have some sort of distance, and then we have some sort of mass. And then so the first moment of mass would be md. That would be like, okay, I have a mass out here, just like I have a force out here, a distance d, but we have the second moment. So we have md squared. We have mr squared. This is the second moment of mass. And that's where that term comes from. Hell yeah, so we did it. So we have angular momentum is second moment of mass, omega. But now the second moment of mass comes from the fact that this velocity term is because if you have a circle, hell yeah, that chunk of mass is going hella fast. It's got a tangential velocity of omega to its r. Hell yeah. And then if we say momentum of that, well, that's just mass times the velocity of that mass. Alright, hell yeah. So my camera overheated. Had to take a break too. And man, this is so brutal. Well, it's just the fact of like, hey, this is my learning style. It's like, well, I don't want to use the big equations to get, the complex, problems done. If I don't have any understanding of the actual fundamentals of where this stuff comes from. So I think we left off that this is second moment of mass. So we have the mass at a distance, and we're going to square that distance, and that's where that I term comes from. And then we double down on it, and yeah, if you have a circle, you have a chunk of mass that's going hella fast out there, and then so that term, yep, and I actually forget where we left off. But cool, so we have this, we know what I is, you know what I mean? I is going to be the radius squared, mass, mr, it's that mass, and then the distance squared. So it's the mass moment of inertia. Just like force times distance is moment of force. Force times distance squared is second moment of force. Mass times distance, r, is moment of mass, first moment of mass, and then mr squared is second moment of mass. And that's what we call the moment of inertia, second moment of mass. Cool. All right, so and then for our problem, and we just did this. We have a mass that's 1 kilogram. So our I is 1 kilogram. Sorry, 1 kilogram. And then our radius is 0.5 meters. And then we're going to square it. So we're going to have 1 kilogram and then 0.5. That's like 1/2 squared. And again, that's like 1 squared divided by 2 squared. That's 1 divided by 4. So hell yeah, it's 0.5 times 0.5 is 0.25. So we get an I of 1 force, and this is going to be kilograms meter squared. You know what I mean? Because that's mass, second moment of mass. So you get a distance squared. So that's the units on it. All right, and then so let's go back to our moment. For this scenario, we said our moment was 0.5 Newton meters, and we said that's going to be equal to I alpha. Our alpha we found out to be 1 radian per second squared, and so that's going to be 1 radian per second squared. That means that this I has to be 1/2. That's where I thought I made a mistake, because it's not. second moment of mass is going to be 1/4. So yeah, so we made them. That's good because we're making the same mistake twice, and I could go back to my notes, because yeah, even right here in my notes, the radians per second final minus initial was not 1 radian. It wasn't 1. The angular velocity was 2 radians per second. So we started with an angular velocity of 0 radians per second, and then we got to an angular velocity of 2 radians per second. That should be where my mistake is. I'm just bummed that I made it twice. And now, you know, it's hella busy. My brother would have a nightmare. He has to do his problems just on like the wall, you know what I mean? Just like hugely spaced out, huge sheets of paper. But I kind of like to, you know what I mean, get the room dirty and then try to live in it for a couple weeks before you just go insane. But anyway, yep. So let's find the error, because right here we have a discrepancy. If we definitely know that our moment of inertia is 1, so we have this. Our moment is going to be 1/2 on that side is equal to 1/4 times alpha. So our alpha hella has to be 2 radians per second squared. So let's start fresh, and we're going to do this. So we started out with something like this. All the forces are 1. All the masses are well, in this case. You know what I mean? I guess in this example, you know, we want our mass to be 2 kilograms. But we made it something simpler where we did this. So now we have 2 masses and then 2 forces. And then we even took that simpler and just said, hey, well, let's just take this mass of 1 kilograms, put a force of 1 Newton on it, and this is 0.5 meters. Yeah, so let's just go through the whole process again, because we can do it fairly fast, and then we can hopefully find our mistake. So we have F equals ma. That means that our acceleration is going to be this force on that mass, so it's going to be 1 Newton divided by 1 kilogram. And we know that this 1 Newton is 1 kilogram per meter per second squared divided by 1 kilogram. So that is going to be the definition of 1 meter per second squared. It's going to change velocity in 1 second. So we're going to go t0 to t 1 second. So we're going to get a velocity at t equals 1 second of 1 meter per second. Okay. Cool. That means we have a velocity average. Yeah, hopefully I'm not messing up right there. I don't think so. You know what I mean? We have an acceleration of 1. 1 Newton, 1 kilogram. That's definitionally what F equals ma is. Well, no. The acceleration is F divided. You know, can't mess that up. Acceleration is F divided by mass, so it's the force divided by mass, and we got that. 1 divided by 1 is 1. Definition of acceleration is change in velocity every 1 second. So we're gonna go from 0, velocity initial 0 meters per second, to 1 meter per second. Velocity is 1 meter per second. Therefore, average velocity is 0.5 meters per second, and we went for a time of 1 second. So our distance traveled is 0.5 meters. We know in this case that if we go 0.5 meters, it's going to be 1 radian. So we're going to have an angle of 1 radian. Okay, hell yeah. So now when we go to here and we find our angular radians per second, well, the definition is change in angle, change in time. But again, this is average, you know what I mean? Hopefully I'm not messing that up. So if we, in 1 second, if we're going from 0 to 0.5, yeah, that's right, 0.5, oh, hell yeah. Holy Toledo. I'm so used to using unit circles. So there's the error. You know what I mean? It's so fascinating to find errors. And that's going to be the classic case of my videos, is like, you know what I mean, spot the error first and do a timestamp on it. But obviously you can just watch it all the way through and then point out the error. But yeah, in the comments, if that drives you insane, yeah, please put a timestamp to my errors. I'm not going to. It's just not my MO. I would rather just talk into the camera for hours. It's my therapy. If you want to learn something along the way, that's your deal. So I appreciate the give and take. So sweet, yeah, holy hell. So the definition, this is where radians suck, because they're very, yeah, what the hell is 1 radian? 1 radian is, definitionally, it's an angle. It's an angle. And it's if you have a radius. Whoa. We said, if I know that I have 1 radian, and I multiply it by the radius, I get arc length, S. So what we did is we found arc length. We said we were going to go 0.5 meters. Cool, so we have this side. So, you know what I mean, we have this 0.5 meter side. We don't know the angle side in radians. But we do know the radius is 0.5 meters. So hell yeah, look at that. So we have a radians of 0.5 meters divided by 0.5 meters, which is 1. So we have a radian of 1. And yeah, so that was such a bummer, because I already did this problem this morning, you know, just pretty briefly. But no, we spent some time thinking about it. But yeah, so when I went to here, that was just intuitive to be like, whoa, we have a radian of 1. But yeah, that was a huge mistake of being like, no, we have a radian of 0.5. We have 0.5 radians. So that was the mistake. Apologize. That's why it's so crucial for me to try to take a concept and let's do the simplest problem, because I don't know if it's just me, but I will mess up even the simplest problem. But that's why we have all these backdoor methods to double check, to be like, well, is this what we're getting? And it's like, no, we're off by a factor of 2 somewhere. We need to go find that. And if it's a simple problem, you should be able to go right back and find that. All right, hell yeah. So now we're just on the home stretch. So we have an angle of 1 radian. So our angle initial is 0 radians. Our angle at t equals 1 second is 1 radian. So now our omega average is change in angle, change in time. Well, that's going to give us 1 radian per 1 second. Cool. But this is our average. Again, our speed, angular speed initial, 0 radians per second. Angular speed final, well, it's got to be, or at t is equal to 1 second, has to be double this. So we have 2 radians per second. Hell yeah. Now we can get on to what alpha is. Definition of alpha is change in angular speed divided by change in time. So we have omega at t equals 1 second minus omega at t equals 0 second divided by the change in time. And if you want to get techie, this is the time at 1 second minus the time at 0 seconds. So we have 2 radians per second minus 0 radians per second divided by 1 second minus 0 seconds. And I have to write sloppier because else my thumb is going to fall off. Okay, so we have the angular acceleration of 2 radians per second squared. Booyah. Holy Toledo. Okay, now let's go back to our moment. We wanted to figure out that the moments was equal to I alpha. We found that the moment in our equation, you know what I mean? Hey, just that 0.5 meters, mass of 1 kilogram, force of 1 newton, was going to put a moment of 1 times 0.5. So we have a 0.5 newton meter moment on that side. Our I definitionally is a second moment of mass. You can't go wrong now. This is not moment of inertia. It's second moment of mass. Think about it that way. And because it literally is just a property of mass at distance. You know what I mean? But you square that distance because, you know what I mean? And we know where that because comes from, because it comes from angular momentum of saying r cross mv, and v is omega r. So you have 2 r terms and you have a mass term. Because a lot of problems, hey, you just want to do angular speed I, you know what I mean? And then, because angular speed is its own property that's measurable, quantifiable, and now we want to multiply it by something that literally won't change for the problem. If you've identified a disk with some sort of mass and you're spinning it, even with an angular acceleration, hey, that just means it has a angular speed for every time that you give it. Just because it has an angular acceleration doesn't mean that it doesn't have an angular speed. It always has an angular speed at a moment in time. And if it has an angular speed at a moment in time, then we know its angular momentum at that time because it's just radius, mass, and then its angular speed. The radius won't change, the mass won't change, and now we're just good to go. But, like, you can't just hand wave that the I for this is just mass times the radius. Hell no. You know what I mean? We had to do it for the simple. The mass is the angular. This goes back to what angular momentum is. It's like, hey, you've identified. It's like, hey, you have a radius cross product with a mass. You're identifying that mass. You're identifying that mass. That mass has a velocity, and you take the cross product. Which all that cross product means is like, when we're torquing a wrench, all we're interested in is the force that actually makes sense. If I have a force this way on a wrench, it's like, well, don't put 100 pounds this direction and then call it 100 pound-feet. You know what I mean? You can't call it 100 pound-feet. This is 0 pound-feet because it's the cross product. We want force times distance. So if this was force times distance, it's d cross v. You know what I mean? It's the distance vector crossed with the... So even here, line of action, let's say I have the wrench out here now. The wrench is a little bit longer, and now I'm putting a force that way. Well, it sounds like you're not doing a very good job, and then you take this to the extreme. You know what I mean? And then I'm putting a force that way. Well, to the extreme, it looks like you have the same case where you have a wrench, and then you're just putting a force that way. You know what I mean? Well, don't do that. That's putting 0 pound-feet on it. This is 0 pound-feet. So that as this angle gets huge, and if you're just putting in that direction, you know what I mean? So at this case, you know what I mean? Even if you're way the hell out here, I mean, you have this huge lever arm. If you did put that same force, and this is like 4D, well, now you'd have a moment of, your moment would be 4D times force, you know what I mean, or force times distance. Would be force times 4D, you know what I mean. But you put just that crap angle, but it's still in this direction. It's like you're putting a leverage arm of that, and so it's just force times distance. So that's the cross product. Cross product just wants to know, hey, the perpendicular values. So if your distance is out here and you're going this way, it's like, no, I just want to know the perpendicular distance times. So cross product, even if it's D cross F, is D sine of that angle. I apologize. No. It's which one would you actually... Because in this case, you're just like, well, what angle are you taking? You know what I mean? I think it's better just to assume that it's the perpendicular distance from there. But at the end of the day, it's the cross product for a moment. dF is just dF sine theta. You know what I mean? Well, whether the sine theta is hooked into the distance or the force, maybe it doesn't matter. But I think it's hooked into... Isn't it cross product sine? You know what I mean? Because, yeah. Because if... no, is it cosine? Oh, damn it. I'm messing this up. No, it is sine. But what angle are they talking about? I think, yeah, that's the confusing thing. So yeah, let's not dive into the statics aspect of it. But anyway, we want perpendicular distance, and that's what we get when we do angular momentum. We have a distance out to some mass, and then we have a velocity on that mass. Okay, holy hell. well, I think we just need to finish this video. So this I is going to be mr squared, second moment of mass. So I think we have that down. The mass is 1 kilogram, so we have 1 kilogram times the radius of 0.5 squared. So this just turns out to be 1/4, and then we're going to multiply it by alpha, which is 2. Cool. And so let's get some units on this. So we have this is mass of 1 kilogram, radius of 0.5 meters squared, and then we have an alpha of 2 radians per second. So we're going to get kilograms, meters squared, and this is radians per second, 2 radians per second squared, meters squared per second squared. And we know that moment is kind of force times distance. Force is in newtons, distance is in meters. Force is in kilograms, meters per second squared, times meters. So yeah, we should get something kilograms, meters squared, second squared. And we do. So we get definitionally what the moment is. And hell yeah. So I feel like we're dumber. But anyway, we did it, and I thought this was going to take 5 minutes, but it didn't. But I learned a lot. I learned how to make a mistake and catch my error, that's for sure. And I learned just a little bit more about moment of inertia, second moment of mass, moment of inertia. And we learned that if you do have a moment, you are going to induce you're going to induce a rotational motion. That's why I've always said, hey, F equals ma. If you've identified a force, you know what I mean, on a mass, and you only have one of those forces, you're going to have motion. I'm going to call this side motion, you know what I mean. So if you have a problem where you're like, whoa, something's in motion, the first question you need to ask is like, was it stopped? Or was it slower than it was? Is its motion changing? And usually it's yes. For anything in the known universe, it's really difficult to get things to go in the same direction. Yeah, hell yeah. It's very difficult to get a mass going with a velocity in the same direction and not changing its velocity. So just calling this motion, hell yeah, that's a pretty decent thing. Unless you're a skydiver, you will at terminal velocity, and you know what I mean. You've identified motion, but then that second question is, well, is there a change in velocity? You know what I mean. And so maybe the question is no. But any problem that starts where you have something at rest, whether it's a circle on a hill, well, cool. This is going to be the next problem that I'm going to, just do a horrible job of spending 2 hours on and just making, breaking it down in just its simplest forms. But I don't mind doing that. But what we're going to find out is that sure, you have an omega 0, but then eyeballs on it, sure, you're going to have some sort of motion later. So you're going to have a change in angular speed. And so that gets back to here. If you identified a moment, you know what I mean? If you've identified this situation, then we know that it's equal to I alpha. We just wanted to get one more step in the right direction, because where this came from was doing statics. Is like there's plenty of statics books that say, yeah, sum of the forces is equal to mass times acceleration. But then when you get sum of the moments, they don't. They just say, hey, the sum of its moments are 0. They don't even put anything out here. But you can also say, sum of the moments, because the moment is force times distance, well, that has to be equal to ma times distance. You know what I mean? So you could do that. You could do sum of the moments is equal to mass times acceleration times distance. And I think that's what we did. Let's grab one more sheet of paper and kind of polish this thing. Because we took a very simplified mass, 0.5 meters, and what did we say? We said we had a force of 1 Newton, and so we've identified, so the sum of the moment side was going to be 0.5 Newton meters, and then we're going to say that's equal to 1 kilogram times acceleration times that distance of 0.5 meters. Cool. So this is going to divide by 0.5 meters. Meters cancel, and then we'll divide by mass, 1 kilogram, and so you're going to have 1 Newton per 1 kilogram, and that's going to be acceleration. And we just did this, and we see that that's going to be 1 Newton is 1 kilogram meter per second squared divided by 1 kilogram, and we have meters per second squared. So I guess you're going to say that sum of the moments is equal to force times distance is equal to mass times acceleration times distance, but now it's equal to I alpha. If you do have, so in our problem, sure, we've identified that there is going to be an acceleration on that from the perspective of using a moment. Yeah, we used a moment, and then we said that was equal to MAD. That's what we did right here. So yeah, but for pure rotation, we know now the sum of the moments is equal to force times distance is equal to MAD is equal to I alpha. And in a lot of books, they'll just say sum of the torques is equal to I alpha. But the torques are kind of the moment generated at each point. It's just fascinating to me that you'll spend your entire year in statics talking about moments, and then, sure, yeah, some of the moments are equal to 0. But if the sum of the moments aren't equal to 0, I don't see why it magically becomes, a torque. It's just the moments aren't equal to 0. I think categorically you can still say some of the moments are equal to I alpha. And that's what I'm going to do for my problems. The first problem I'm going to do is identify that a circle, you have 0 velocity right here, you have its mass right there, so it's the same thing as maybe a mass on a stick, and you have mg, and guess what? Here's your pivot point at your 0, and it looks like you do have some sort of torque. You have some sort of force in that direction. You do have a force in this direction, not putting a torque. And I don't even know why I'm calling it a torque. Maybe we should be calling it a moment. So some of the moments are going to be mg, probably cosine theta, if I got that right, depending on where your angle is. If this is the angle of the ramp. Don't quote me on that, the way my drawing is. But anyway, you're going to have some sort of fractional representation of mg due to sine or cosine. And the distance away is going to be r, so you're going to have mgr, and then some sort of fractional distance. That's going to be the moment, and that's going to be equal to I alpha. And in this case, we can even take a circle and just say, well, let's put all the mass right there, and then so we're going to have mr squared, and then alpha. So we'll have mr squared alpha. And hell yeah, masses will cancel, one of the radiuses will cancel, and we can find alpha is equal to g cosine theta divided by r. You know what I mean? And I don't know, we just do simple things like that. But we'll actually put numbers on them and turn rotational problems as simple as possible, starting with the moments and knowing that that's equal to I alpha, or some of the moments is just equal to MAD. It's just that F equals MA, but if you have FD, that's going to equal to MAD. Alright, holy hell. So I kind of want to be done with this one. So thanks for joining me. This was probably brutal. It's just my ability to teach myself. But there you go. You know what I mean? You were along for the ride. I appreciate it. So thanks for joining me, and that's a video.